So, good evening, everyone. Welcome. So we were doing, so we were solving lots of inequalities and pretty much covered 70% of them. And so the homework was to solve QM or prove QMAM inequality with Chevyshev's, which is this inequality. Right. So Chevyshev kind of says if you have a dot product, an average of the entries of a dot product between two vectors, then it's the product of the averages of those two vectors. Now, do you remember what is QMAM inequality? Well, let's go back. So this is the quadratic mean. And this is the arithmetic mean. So let's write them down in a new page and start today's class. So AM-QM inequality. So it says sum over xi squared, which is x1 squared, x2 squared, up till xn squared. Average of that, square root over that. This is greater than or equals to x1, x2, x3 up till xn by n. Okay. Suppose we take the first vector is x1, x2, x3 up till xn by root n, root n, root n. This is the first vector. And the second vector is so x1 by root n, like the same thing. x2 by root n up till xn by root n. So we take both the vectors as same xi by root n. So if we take the sum of the product of the average, we get okay. Maybe we don't need this. It will just cancel out, by the way. So x1 this is less than or equal to square root of sorry. Right. So this is by Chevyshev's. Now we can take square root both sides and get our required AM-QM inequality. Right. So this is one liner. Next. So we have already covered, till now we have covered these inequalities, the AMGM, QMHM family. Next, we have covered rearrangement. We have covered Nesbit and Shevaishep. Oh yeah, we have also covered Jansen. Anything else? So Jansen can be generalized into a function, sorry, an inequality called Minkowski. Right. Sorry, not Minkowski. It's called Karamata, but I can't find it here. Okay, first let's move on to the next most commonly used inequality. That's the Cauchy-Schwarz inequality. So Cauchy-Schwarz. So whenever you have sum of the squares and product of the very same things, people mostly try to apply Cauchy-Schwarz inequality. So the idea is kind of similar to Chebyshev's inequality, but so if you have observations x1, x2, x3 up to xn, and observations y1, y2, y3 up to yn, so you can kind of think of it same as a vector, two vectors. You can say you can take the norm. So the norm of a vector is the L2 norm of a vector is defined as the sum of the squares and square root of that. So you can take the product of the two norms. This is greater than or equal to the dot product squared. No, sorry, I guess not squared, right? So if you had squared it on the left hand side, this would have been squared. Else it's just that, okay. So it's x1 squared plus x2 squared up to xn squared times y1 squared, y2 squared up to yn squared is greater than or equal to x1 y1 xn yn squared. Sorry, xn yn. Yeah. If you take square root on the left hand side, this is square root of this. An equality so condition for equality. So you can see it's greater than or equal to. So for some values of xi and yi, this equality must hold, right? So this is the condition for equality. x1 by y1 equals to x2 by y2. So the vectors have to be collinear to start with, so that we can have equality and Cauchy-Schwarz inequality. You can easily check by plugging this into the equation with inequality. So if both x and y are the same vector, then the norm product of the norms will be just the norm squared. That is greater than or equal to the same thing on the RHS. So this holds. Now, as for the proof, you can think of it as if you had two vectors in n dimensions, x and y, then you know the dot product of those two vectors is mod x mod y cos theta. And this cos theta is in between -1 and 1. So mod of cos theta is in between 0 and 1. And so you can multiply both sides with mod x mod y. Sorry. And replace this with x dot y. Then you get Cauchy-Schwarz inequality. Now the question is, so this is only valid for for 3 dimensions and even for 2 dimensions. What about in other dimensions? So we don't know exactly if triangle inequality is valid in n dimensions. So this basically says if you have two vectors and take the dot product, which is the projection of one onto the other, this length is always smaller than any of the two vectors. So we can use quadratic formula for this one. So we can think of a quadratic like this. So that px we are quadratic polynomial ax squared plus minus bx plus c. A, B, C are cleverly chosen to be like A is x1 squared plus x2 squared up till xn squared. B is x1 y1 x2 y2 up till x and yn. And C is y1 squared y2 squared up to yn squared. Now, observe that we can write px as x1 minus, sorry, so x1x minus y1 squared plus x2x minus y2 squared, like that up till xnx minus yn squared. This is because we can take the ith terms from each of the three you can say expansions and plug them up into a single perfect square. So now, as we know, sum of n perfect squares for xi's, yi's, and x are all reals. So this will be greater than or equal to 0. Whenever we have a whenever we have a quadratic which has roots only in the positive reals, then how should its plot look like? So it should look like something like this. So polynomials or quadratics in general have a parabolic graph. So either it can be this, or it just touches, like this. So in both these two cases, there is a value which is okay. So this, yeah, this is not crossed. So in this case, the last one, this case, we have values which are negative, right? In the minus y axis. So that can't be true. So this can't happen. So we can only have this case or this case, in either of which the quadratic doesn't really have a real solution, or even if it has, it's a degenerate solution. So the condition for a quadratic to be positive everywhere is so px greater than or equals to 0 implies discriminant of p greater than or equals to 0. The discriminant of p is b squared minus 4ac. So this is greater than or equals to 0. That implies 4 times sum over xi yi squared minus 4 times sum over xi squared, and c is sum over yi squared. This is greater than or equal to 0. We can cancel out the 4's and we get a required Cauchy-Schwarz inequality. Oh, sorry. So I got the inequality wrong. So the roots have to be complex, right? They don't have a real root in this case, so it's less than or equal to 0. Equal to 0 will be the case when it just touches the real axis and x-axis and has a degenerate solution. So proved. Okay, so let's practice some problems. So some easy examples might be a square b square a square b plus b square c plus c squared a times ab squared plus bc squared plus ca squared. Show that this is greater than or equals to 9abc squared. It's basically 3abc squared. Right, so I guess it's obvious how to solve this. You will just have to pick the x and y, x's and y's, and you can see if you take the corresponding product, it's a cube, b cube, right? So So you can take it to be a squared b, b squared c, c squared a, and bc squared, ca squared, ab squared. Now they all the product becomes all of them multiply up to a square, b square, c squared. And on the right hand side, the sum up to 3a square, b square, c square. But they have a 9 there on the right side. So okay, so why is there a 9? I guess it's a printing mess. It's a typo. It's clearly it should be 3. So take x. So take x as this vector and y as this vector. Next we have so x by 2 plus y by 3 plus z by 6. This less than or equals to x squared by 2 plus y squared by 3 plus z squared by 6. So again, you can see you can break this down into break it down into x squared, y squared, z squared, and 1 by root 2, sorry, 1 by 2, 1 by 3, 1 by 6. The left hand side will match, but not the right hand side. So maybe we should simplify this a bit before applying Cauchy's rules. We'll get 6 as the LCM and 3x squared plus 2y squared plus z squared, 3x 2yz. You can cancel 1 6 out, so it's 6 times now you can take 1 plus 1 plus 1 plus 1 plus 1 plus 1. This is the first vector, and x squared plus x squared plus x squared plus y squared plus y squared plus z squared as the second vector. So the dot product will be, so the first vector x is 1 1 1 6 ones. The second vector is x x x y y z. So the dot product is x plus x plus x plus y plus y plus z, which is 3x plus 2y plus z whole squared. These are some easy examples, pretty straightforward. So you can prove Tito's inequality with this Cauchy-Schwarz inequality. I guess you might never have heard of this new inequality, but this is basically the more commonly called power mean inequality, I guess. So sum over ai squared by bi squared, that is a1 squared by b1 up till n squared by bn. So that is greater than or equal to a1, a2, a3 up till an whole squared by b1 plus b2 up till bn. So the condition is ai's and bi's must be positive reals, which is true for all the previous inequalities too. Not the Cauchy-Schwarz though. Proof. I guess I should give you 5 minutes to think about the proof, as it's kind of one-liner with Cauchy-Schwarz. So you have to first rearrange the inequality a bit before proceeding with Cauchy-Schwarz. I will mute for 3 to 4 minutes. After that, we'll discuss. Okay, so at first sight you might be tempted to pick a1, a2, and up till an, and 1 by b1. Okay, square root of 1 by b1, square root of 1 by b2, up to square root of 1 by bn as the observations. And then after multiplying, you would quickly realize that this isn't quite catching up, right? If you take the square of this, it will match the left-hand side, but that's the wrong side since this is the dot product and it should match the right-hand side instead of the left-hand side. So let's first bring this denominator up there on the left-hand side. So this inequality is true if and only if so b1 plus b2 up till bn times a1 squared by b1 plus dot dot up till en squared by bn is greater than or equals to a1 plus a2 plus a3 up till an whole squared. Now you can take b1 square root of b1 square root of b2 up till square root of bn as x, and a1 by square root of b1 up to an by square root of bn as y. And the rest is, you can see the dot product is, the bi's cancel, square root of bi's cancel out, you get a1 plus a2 up till an. So we are done. So that was it, T2's inequality. So other major inequalities. Okay, so this is not exactly inequality, but some people do name it as Young's inequality. This is a consequence of weighted AMGM inequality. You have, so x and y are two observations. You have x power a power 1 by a and y power b power 1 by b is less than or equal to x power a by a, plus y power b by b. This is by gm less than or equals to am, the weighted version. So this is weighted AMGM inequality, right? So the observations are X and Y, and the weights are A and B. Now, from that, we can say if 1 by A plus 1 by B oh, sorry. So, yeah, so if 1 by A plus 1 by B is indeed 1, then we can say xy is less than or equals to 1 by A x power A plus 1 by B y power B. So this is the Young's inequality. And the proof is the first line that we just uh, started with as AMGM, weighted AMGM inequality. Right. I hope you all got the proof, and we started it with in the reverse way. And so like this, you can also start have the same condition. So that 1 by A and 1 by B is equal to 1. So they add up to 1, and you have two observations, two vectors, x1, x2 up till xn, and y vector is y1, y2 up till yn, just like Cauchy-Schwarz and Chebyshev. And just like Cauchy-Schwarz, we are taking the dot product on the left-hand side. But instead of taking the power of squid and the norm on the right-hand side, the L2 norm on the right-hand side, we're taking the LA norm. So it's power A power 1 by A and yi power B power 1 by B. So this is here called the LB norm and LA norm. So an LP norm in general, LP norm of vector x is defined as x1 squared, x2 squared, up till xn squared. Sorry. So x1 power p, x2 power p, xn power p whole power 1 by p. So if you substitute p equals to 2, you get an L2 norm, which is just our regular Euclidean norm. So this is the product of two norms, which is greater than or equal to their dot product, which is the same as Cauchy-Schwarz, but the norms can. So Holder's inequality says the norms can vary, but the inequality is the same. And the proof is with this above. So this is the Holder inequality, the generalization of Cauchy-Schwarz. or CS. So this he's a Polish guy, so I guess he's a Hungarian. I'm not sure. So there are two dots, X marks over O. And well, the proofs we can use. Okay, we can use Young's inequality to say so from Young's inequality we can say xi power a by a, yi power b by b, xi yi. Right. So we can add every like get I. So we can vary I from 1 through n and get n such equations and add them up. This is what we get. We know 1 by a plus 1 by b is 1. So just a minute. Call. Sorry, I was getting a phone call, so I had to attend it. Okay, so I was proving the Holder's inequality, and so we got this far with Young's inequality, and what to do next? So let's first assume that sum over xi power a and sum over yi power b is 1. This is a weird assumption, I know, but let's go on with this. We can later substitute xi, yi to be some ratio, and it's So with this, we can say xi yi is less than or equal to 1 by a plus 1 by b, since they add up to 1. Like xi power a whole sum is 1, so it's 1 by a, and 1 by b is y power b. So this is from the condition that we assume that first is also 1. So we have got 1 is greater than or equal to xi y. 1 is the upper bound of the dot product. Now we can substitute, say suppose we want to substitute something fancier. So what if xi power a is a instead and yi power b is b instead? Then we can take a new value of xi and correspondingly the x vector as xi power a by 1 by a, yi dash as yi by 1 by b power 1 by b. So basically normalize the vectors xi and yi. So now also if we sum up xi bar, we get sum over xi by a power 1 by a. So if we sum over xi power a, xi dash power a, we get xi power a by a power 1 by a power a, which is a xi power a by a, and a is, as we defined, xi power a, which is 1. So now we can say xi dash yi dash is greater than or equal to 1 from this one, from star. Substituting the values of xi bar and yi bar, we get its xi yi power. So yeah, xi yi by a power 1 by a and b power 1 by b, which is less than or equals to 1, which implies sum over xi yi is less than or equals to a power 1 by a and b power 1 by b. Substituting the values of a and b, it's sum over xi power a whole power 1 by a and yi power b whole power 1 by b. And we are done. So same as Cauchy-Schwarz inequality, equality in this case holds only when xi power yi have a constant ratio for all I. So that was Holder's inequality, the generalization of Cauchy's inequality, Cauchy-Schwarz inequality. There is a further generalization of triangle inequality. So Minkowski. So this is a generalization of triangle inequality. So what does a triangle inequality say? It says if we have a triangle, which by the way we can also think of as three vectors, two pointing in the same clockwise direction and one anti-clockwise direction. Right, so suppose this is A, this is B, this is C. Sorry, this is B, and that is C. So we know A plus B is C from the rules of vector addition. And triangular inequality says that the sum of the absolute values of any two of them is strictly greater than the third. This strictness only vanishes when this isn't a triangle and all the three vectors are same. That is when A and B are collinear. A like equality holds. Equality holds when A is equals to plus minus B. This time, so this is the triangle inequality, and the Minkowski says the same thing, but we use the LP norm and LQ norm instead. So sum over AI BI power P whole power 1 by P. This is less than or equal to sum over AI power P whole power 1 by P times sum over BI power P whole power 1 by P. AI BI's must be positive, mind you, and P has to be greater than 1. Otherwise, these LP norms actually diverge. Okay, so now proof. We can use Holder's inequality for proving this one. First, look at this term AI plus BI power 1 power P. We can write it as, so we can take one AI and BI, one AI plus BI common, and multiply it. Right, and then add sum up I from 1 through n on both sides. So we got this left-hand side without the 1 by P. So now we can apply Holder's inequality to each term of the sum on the right-hand side. So applying Holder's inequality term-wise, we get, so the observations in the first case is AI and A1, A2 up till AN, this one, and A1 plus B1 whole power P minus 1, A2 plus B2 whole power P minus 1 up till AN plus PN whole power P minus 1. So these are the two observations. And Holder's inequality says the dot product, which is the first term on the right hand side. This is less than or equal to the LPth norm. By the way, we can take P equals to P and Q equals to 1 minus P. Right. No, sorry. We have to take Q equals to P by 1 minus P. That is, we have to make 1 by P plus 1 by Q 1. So that is 1 by Q is 1 minus 1 by P. So Q is P by P minus 1. Okay, sorry, it's P by P minus 1. So this is sum over AI power P whole power 1 by P and sum over AI plus BI power P minus 1 times Q whole power 1 by Q. Similarly, we get for the other term. So for that, let's see what this actually evaluates to. We know. So Q is P by P minus 1. So this, the second term becomes one by Q is P by P minus 1. Right. So this is for the AI, the first term, AI into API power 1 by P minus 1. Similarly, for the second term, BI times AI plus BI power P minus 1. Correspondingly, our observations are sum over BI power P power 1 by P. And AI plus the same one, so it would be sorry. This is not P by P minus 1, it's the reciprocal of that, so it's P minus 1 by P. If we add these two, so this is 1 and this is 2. So 1 plus 2 implies so we have sum over AI plus BI power P, which is equal to sum over AI BI plus BI power P minus 1 BI sum over BI times AI plus BI power P minus 1. This is greater than or equal to, we can take common AI plus BI power AI plus BI power P minus 1 by P, which is 1 minus 1 by P. Times sum over AI power P. So I forgot to add a 1 by P here. Whole power 1 by P plus sum over BI whole power 1 by P. So did we get our required inequality? So what was our required inequality? So required inequality had 1 by p both. The left-hand side had sum over ai plus bi whole power p, whole power 1 by p. So let's take 1 by p both sides. Okay. So this thing and this thing, we can, oh sorry, actually we could just have brought it to the left hand side. So no need to divide, sorry, no need to take 1 by p power. Just bring this thing to the left. So ai bi power p whole power 1 minus 1 by p. Which is 1 by p. Proved. Okay. So we have almost finished inequality. So let's try out with some problems. So problems. Uh, try to show. Okay, try to show sine a by 2, sine b by 2, sine c by 2 greater than or sorry less than or equal to 1 by 8, where ABCs are the angles of a triangle, so they add up to pi. Number 2 is sine A, sine B, sine C less than or equals to 3 root 3 by 8. And also show sine A plus sine B plus sine C is 4 cos E by 2 cos P by 2 cos C by 2. Solve these three problems. I will be back in 10 minutes. So I guess 10 minutes are over. And as for these three problems, so we know tan A plus tan B plus tan C is equal to tan A plus tan A tan B tan C. So we know this. Right. Now from this we can start off by let's try to put the middle one first. So on the left hand side we have got sin A sin B sin C, cos A cos B cos C. So yeah, they can show it in the normal way, like clubbing two of the terms together. So this is 2 sine A plus B by 2 times times cos A minus B by 2 plus sine C. Right, so then this is, I guess you can write A plus B by 2 as pi by 2 minus C by 2. Cos is as it is. This sine C can be written as 2 sine C by 2 cos C by 2. And now this is also a cos, so the 2 cos C by 2, you can take common, it's cos A minus B by 2 plus sine C by 2. Now you can use, so you can again write cos C by 2 as sine C by 2 as cos A plus B by 2. And again use the formula for the sum of 2 cos as 2 cos A plus B by 2, which is E cancels out B by 2 and cos E by 2. So it's 4 cos A by 2 cos B by 2 cos C by 2. So this is the first inequality we got, and for the rest we can take observations as tan A, tan B, tan C. So these are our observations. Applying AMGM, we have tan A plus tan B plus tan C by 3 greater than or equals to cube root of tan A, tan B, tan C. But we know tan A plus tan B plus tan C is again tan A, tan B, tan C. We take, so this is tan A, tan B, tan C power 2 by 3, which means it's 3 power 3 by 2, bounded below by 3 power 3 by 2. That is 3 root 2, 3 root 3. Now we have to show, so 3 root 3 by 8, okay. else we need to show? So to show sine A plus sine A sine B sine C is greater than or equals to 3 root 3 by 8. So we first have to show the that cos A plus cos B plus cos C is less than or equals to 3 by 2. Why is that? We can again go out with the same pairing technique. Cos A plus B, that is 2 cos A plus B by 2 times A minus B by 2 plus cos C. C is again pi by 2 minus A plus B by 2. Sorry, first we have to make it C by 2, so 1 minus 2 cos or sine squared. Yes, it will go and becomes cos. So it's 2 sine C by 2 cos A minus B by 2. So we can write sine square C by 2 as cos squared A plus B by 2 and take cos A plus B by 2 common. And we get okay, just a minute. Instead of doing this, we should keep this sine squared C by 2 and make this sine C by 2. Taking common sine C by 2, you get okay, let's assume this is equal to x. Then we have, if we bring everything to the left hand side, 2 sine squared C by 2 minus 2 sine C by 2 cos A minus B by 2 minus plus x minus 1 equals to 0. So this, as you can see, is a quadratic in sine square c by 2. And this has a root which is real. So we know the discriminant has to be greater than or equals to 0. So from that we can derive an inequality. So that inequality is p squared, sorry, minus 4ac greater than or equals to 0. 4 gets cancelled. So 2x minus 1 greater, less than or equal to cos squared a minus b by 2. We have, so this is bounded above by 1, so 2x minus 1 is, x minus 1 is half, implies x is 3 by 2. I mean, x less than or equal to 3 by 2. And x was the value of cos a plus cos b plus cos c. So now once we have got this inequality for the cosines, we can use this identity. That's the identity is cos A plus cos B plus cos C is equals to 1 plus 4 sine A by 2 sine B by 2 sine C by 2. This is bounded above by 3 by 2. So 3 by 2 minus 1 is the upper bound by 4. The upper bound for sine A by 2 sine B by 2 sine C by 2, which is equal to half by 4 and 1/8. Are we done yet? No? We have to. Not for the half angles, you have to show for the full angles. So if we break it down, sine A by 2 sine A sine B sine C is 2, 2, 2, that's 8. Sine A by 2, sine B by 2, sine C by 2 times cos A by 2, cos B by 2, cos C by 2. So we already have the bound for the sine half angles. For the cosine half angles, we can let's see what we can do. So to find an upper bound, we can represent cos A by 2 plus cos B by 2 plus cos C by 2. Or since we already have this, we can say cos A plus cos B plus cos C is less than or equals to 3 by 2 implies 1 minus 2 sine squared a by 2 sine squared b by 2 sine squared c by 2 less than or equals to 3 by 2, which implies 3 minus 3 by 2 by I guess cos should be better. So it's 2 times less than or equal to 3 by 2. We add it, we get 9 by 2, 9 by 4. This is cos squared a by 2, cos squared b by 2, cos squared c by 2. And so this is, if we consider as the arithmetic mean, this is greater than or equal to 1/3 of 3 times 1/3 of cos a by 2 cos b by 2 cos c by 2 whole power squared. So this is 9 by 4. So 3 by 4 greater than or 3 by 4 whole power 3 by 2. Yeah, 3 by 2 cos a by 2 cos b by 2 cos c by 2. So the upper bound is 3 by 8. Is that right? Yeah, it seems like. And using that, 8 sine a by 2 sine b by 2 sine c by 2 cos a by 2 cos b by 2 cos c by 2. This 3 terms is greater than or equal to 3 by 8. These 3 greater than or equal to 1 by 8. And this is 8. So the whole thing cancels out. So the whole thing is greater than or equals to 8 times 1 by 8 times 3 by 8, which is 3 by 8, as we are required to show. So we have shown this. We have shown this. Right. Okay, and we are also shown this. So we are done. Sorry. It's a bit early, but I'm not exactly feeling much well, so I will want to end the class right here. Okay, so yeah, good night, everyone. We will meet next week. Sorry for this.